counterpart to detect the electromagnetic counterpart to the merger of binary black holes. But of course, if we can detect them even prior to merger, it would be even better to trigger some follow-up. Now the question is basically, how do we manage to do that, and how do we manage to distinguish binary black holes from any other type of sources? And here I will be talking about binary black holes that have some validity for LISA as well as for PTA. So if we want to predict the electromagnetic signatures of pre-merger binary black holes, there are different ways to do it, and in particular to model the fluid around the binary. One way is to use classical Newtonian gravity. That's what has been shown, for example, by Alessia. That's really useful because then you can typically scan the parameter space, let's say, quite easily, and you have a way also to compute the evolution of the system on really long time scale, and therefore reach some kind of pseudo-stationary state. So that's pretty robust. Of course, something you don't have in Newtonian gravity is actually the general relativity effects that will have an impact on the gas, but also on the observations. I mean, we all are familiar with this emission map computed around a single black hole. So if we want to take into account those GR effects, the most complex but also complete way to do it would be to actually solve the Einstein's equation. But that's really computationally expensive, and that's so expensive that actually you cannot evolve the system on hydrodynamical timescales of interest, at least. So we chose a third possibility, which was to actually use the GR-MEVA code and first extend it to dynamical spacetimes, because here we will be therefore talking about dynamical spacetimes, and then to implement an analytical metric, which is approximate, and which is, for this work, only valid in the region of the circumbinary disk. And just to show you what it looks like, this is one component of the metric. And this is typically, if you take only the first term, that's what you would get with a Schwarzschild metric. And you can see that all the rest of the terms, this is for black hole 1, and the same is here for black hole 2. This is what the additional complexity to model a binary and not a single black hole. But despite this complexity, it's still much, much cheaper than solving the Einstein's equation. So that's the method we will choose. And our only restriction is that we can only focus on the circumbinary disk so far, and we cannot model the binary as it becomes relativistic, meaning that there is some orbital separation below which we cannot model the system. So using this framework, we can evolve the hydro equation in 2D here around an equal mass binary. And here I show you the surface density in such a simulation. We noticed some structures that have been presented earlier by Alessia. For instance, you have a cavity, you have some spiral arms, and you have this asymmetry in density that grows at some point, which is called the lump in the community. And what we could do is then to compute from this some synthetic observations using the GR ray tracing code Giotto in the same binary black hole metric. And here for the temperature, we used a really simple model where the temperature only depends on the local density. And when we do that, we can compute the emission map as a function of time, as a function of the frequency as well, which evolves like this with respect to time. But actually, as most of you know, we are talking about unresolved sources. So actually, the actual observation we will have will be an integrated flux over the source extent, which actually translates into this light curve variability. So here, what we have is actually a periodicity in the light curve, which is due to the relativistic Doppler boost that makes that the dense and therefore hot in our model, hot structures that go in your direction, in the direction of the observer, appear brighter, and whenever they recede from the observer, they appear dimmer. And in our case, we have two types of structures that are visible. There is the lump that is the most that is the hottest and brightest structure we find, and are also the spiral arms that produce this smaller amplitude and smaller period oscillation. We could actually try to extract, let's say, the essence of this light curve and the main ingredients to actually propose a toy model to reproduce the light curve, so that you don't have to run an expensive simulation every time you want to fit some observations, for instance. So the idea was actually to create and compute the temperature distribution of a disk in which you would have only some warm spiral arms and a warm lump. And actually, if you do that and compute the light curve, well, you basically get the same oscillations. And what we proposed is that you can actually reproduce the main light curve features using a standard, let's say, an average flux, on top of which you have two sinusoidal modulations, one at the lump period, which is a few times the orbital period, and one at the period of the spiral arms, which is half of the orbital period. And here, the dominant one is the one that comes from the lump. So that's something that can be really useful for observers whenever they want also to anticipate, for example, the timescales that we could probe at the same time as ELISA is observing the system. Now, if we want to actually to observe those signatures, we need to focus on one band in particular. So here, actually, what we show is that the lump, as it orbits, it's actually restricted to the hottest region of the circumbinary disk, and therefore it's associated with spectral changes that only occur in the highest frequency part of the spectrum. Here, this is, for example, for these parameters, this is between the UV and the X-ray bands. But on the right, I show where is this standard, where is this optimal frequency to observe the lump modulation as a function of the binary black hole mass from LISA sources to PTA sources, and as a function of the time to merger, or equivalently of the orbital separations. And what we find is that if you focus on the circumbinary disk, typically it will peak in the UV or in the optical for very massive systems, which are typically the systems that Vincent talked about, just for the circumbinary disk emission. So this is for the circumbinary disk if the binary black hole is in circular orbits. But now there is more than this. First, there is more than the circumbinary disk. There are likely some individual disks that will also contribute to higher energy. But then there is also the impact of the inspiral, and typically the fact that as the binary approaches merger, it's possible that the gas can flow directly from the circumbinary disk into the black holes, and therefore the two mini disks will actually not radiate efficiently. Second, there is also the fact that whenever the binary approaches, well, there is less and less space, less and less region of stable orbits for the mini disks to even exist. And here you really see it on this sketch as the size of the mini disk reduces as the binary approaches coalescence. That's from a paper by Alicia. So that you can expect that at some point, actually, only the circumbinary disk will remain. And at this stage, well, the in-spiral motion of the binary will be so fast that we are in the so-called decoupling phase, meaning that the binary, the inward velocity of the binary is typically greater than the standard, the reference velocities within the disk. So that the disk, basically the circumbinary disk, has not realized yet that the binary is about to merge. And a natural question we can ask is whether the modulation due to the lump can actually survive in that particular case. So to do that, we run a first simulation in which we reproduce the circular orbit pseudo-stationary state. That's what you can see here on the left. And then we will start from this state to actually restart the simulation, but triggering the in-spiral motion, just like Alicia mentioned also in her talk. And there are different numerical challenges associated with this setup, in particular because we only have a metric that is valid in the circumbinary region, meaning that at the beginning we cannot model the fluid close to the two black holes, and therefore as the two black holes approach each other, actually, the validity region of the circumbinary disk space-time is getting closer and closer to the center of the grid, meaning that we need to actually activate cells, grid cells on the fly as the in-spiral occurs. The second difficulty is that the in-spiral time is really short once you are close to the merger, but if you consider actually larger orbital separation, is getting slower and slower. So actually following the in-spiral from large separation to small separation is really, really expensive. But if you manage to do it, then actually this is what we found. So that you can see that here the white space is much smaller here than here because we activated cells on the fly, and you can see that actually there is still this lump feature, this really strong asymmetry. And the consequence of this is that actually, for the same reason as before, you will have some relativistic Doppler effect acting on the lump emission, as long as you have some inclination with respect to the circumbinary disk plane. But if it's the case, then you actually have a modulation from the lump that survives until really, really close to merger. Actually, in our case, it survives until the end of the simulation. And the end of the simulation for us is whenever the metric is not valid anymore. So basically when the motion from the binary black hole becomes relativistic. And if we translate that into human timescales, it means that actually the lump is observed down to less than a day before the merger. And I will conclude on the fact that the lump indeed survives even post the decoupling stage, as has been also mentioned by Alessia. So in conclusion, so we have found in agreement with the previous studies that the lump can modulate the electromagnetic variability of the circumbinary disk, but we also wanted to go beyond just this result and try to extract the main characteristics of the light curve, and that's why we proposed a toy model to reproduce the light curve. And then in the second stage, we showed, again in agreement with, for example, the paper of Alessia, that the lump survives even in the post-decoupling stage, and she showed it typically, so with her code and with typically different numerical methods from ours. So that's really important to have complementary studies that in the end reach the same conclusion that the lump survives post-decoupling. And since at that stage, it's possible that actually the mini disks might have disappeared, it could be that the last electromagnetic breath from the binary black holes, and in any case from the circumbinary disk, will be actually related to the lump modulation. Thank you for your attention.
Many thanks, Raphaël. We have time for question before the lengthy discussion.
Yes, thank you. Very nice talk. In your last, so this slide, looking to the light curve. So is there some variability from the light curve? Because I don't know, looking to the light curve, it seems to be quite it's difficult to know if there is a periodicity or something like this in your light curve. Is it the case, or?
Yeah, so that's the case. The difficulty is that we are not like in an idealized case, let's say, where the lump period would be exactly the same. So that's why it can be kind of hard to distinguish whether the periodicity is there or not. But actually here, the main periodicity you see is the one of the lump. Although the period and the amplitude of the modulation will in the end depend on the local conditions in the disk.
Okay, thank you.
Thank you. More question for Raphaël? Yeah.
Hi, Raphaël Mate here. Thank you for the great talk. The introduction of the metric, which is dependent on time, does it also introduce new terms in the hyperbolic equations describing the fluid? And if that's so, like, is there any numerical challenge and when they might become stiff due to the high variability, the time scale on which the metric varies?
No, so actually what's kind of great is that even going from a static metric to a dynamical metric, the equations have the exact same form, let's say. What changes is the conservative variables. Like the definition of the conservative variables now also encapsulates something that depends on the metric. And then for your second question, indeed, there can be some kind of like courant constraint that comes from the metric evolution. Yeah, that needs to be taken into account.
Okay, thanks.
Thank you for the very nice talk. I have two more physics questions. One is, so I'm sort of following this you know, from a bit far away this field, but I got the sense that there's also some MHD simulations around, and they're also talking about the lump and everything. So I guess what is your sense in terms of the lump, you know, as compared to, let's say, MHD simulations, and how would the modulation look like? So that's one question, and the other one is, so how radiatively inefficient are these accretion tests? Because you know, I see you're modeling the emission as like black body emission and so on and so forth, and so I wonder what the imprint of cooling would be on the lump, on these overdensities, for example, if that was included in the simulations. Thank you.
Thank you for the questions. So for the first question, I think that the answer is basically here. So regardless of like people including 3D, 2D, GRMHD, Newtonian gravity, and so on, the lump is there for circular orbit binaries. I think that's kind of a robust result. Then for the relative efficiency of the disk and of the structures, I think that's kind of still an open question. Also possibly because it's not like the question was settled even for single black hole disks. So people can use different recipes, let's say, to incorporate heating from shocks, for example, or from alpha viscosity in the simulations. And what's nice is that even though we are using a very simple model for the thermodynamics, we actually get in the end a modulation that is similar to what you could obtain with more complex thermodynamics, like with including radiative cooling, shock heating, and viscous heating. You will get in the end the same shape.
Thank you, Raphaël. Time for one last question before moving to the discussion. No? So if not, so let's thanks again warmly all the speakers of this morning session.